Hello, welcome to today's video on electric fields. Electric fields are kind of a tricky topic. They're one of the last remaining truly somewhat difficult conceptual topics that we'll be talking about. And it's not so much that, I guess what I'm trying to say is, ultimately, the more you see electric fields, the more you will get used to them. It's just that when you first hear them, they are kind of weird sounding. Okay? What I want to do to introduce this is I want you to think about how all the forces that we've learned about so far this year are different than the gravitational force and the electrostatic force, which I'm calling electromagnetic here. That's the proper name, but you guys are more used to electrostatic. Think about how all the other forces are different. The applied force, it happens, an applied force gets generated when a person or some like animal or something pushes on an object. A normal force, when an object is in contact with the surface. Tension, when it's in contact with some sort of string or rope or chain or whatever. A spring force, when it's in contact with a spring. Okay, when some object is in contact with a spring, that causes a spring force. Let's see, are there any others? Friction, an object has to be passing over something, has to be in contact with it. All of those forces require contact. The force of gravity and the electrostatic force, as you guys know them, do not require objects to be touching. They do not require objects to be in contact with each other. Okay? Now that's different. Again, the gravitational force, electrostatic force, do not require objects to be in contact with each other in order for those forces to exist. If two objects were not touching, okay, so for example, applied force, if you're not touching the object, you can't put an applied force on it. If the object isn't on a surface, then there can't be any normal force, and a lot of times there can't be any friction. If an object is not attached to a string or attached to a spring, then tension and the spring force respectively do not exist. So, the force of gravity and the electrostatic force are just a little bit different. Let's talk about what causes those forces. The force of gravity is caused by the interaction between two objects that have mass. If objects have mass, they will have a force of gravity between them. The electrostatic force, Fe, is caused by objects that have electric charge, as we learned in our last topic. If two objects are electrically charged, there will be an electrostatic force between them. So the question is, why do these forces act like this? Okay? These forces are different. There's something strange about them. And it turns out these two forces actually work kind of similarly to one another. Turns out that these two forces work because mass and charge quite literally change the space around them. Mass and charge have the property that they actually alter the three-dimensional space around them. And scientists, that's how we explain why these forces can act when objects are not touching. You know, the Earth is attracted gravitationally to the sun. The sun is not touching the Earth is not touching the sun. How do they interact? It's because both the sun and the Earth, by virtue of having mass, interact by changing the space around them. That is how we explain how these objects that are not touching each other are interacting. Because the Earth and the sun both have mass, they have both altered the space, the physical three-dimensional space around them, and what we observe are the effects of this alteration of space. So this is how scientists explain objects that aren't touching having forces on each other. And there's a name for that. When objects do this, when they alter the space around them, we say that they create a field. Now, the Earth and the sun, by virtue of having mass, alter the gravitational field. And we've talked about gravitational field a little bit because we said, if you look on the reference tables, that one of the other names for acceleration due to gravity is gravitational field strength. Now, we don't really have to talk too much about gravitational fields, but for electric fields, we are going to talk a bunch about those. An electric field is simply the alteration of space created by an electric charge, by a singular electric charge. It only takes one. A singular electric charge will alter the space around it, and scientists are interested in measuring that alteration of space. If we measure this thing called the electric field, which is created by some electric charge, then we can determine how other charges will react to the field. And by how they react to the field, what we're really meaning here is how much force gets applied to these other charges if we were to bring them in. Now you might be saying, this sounds like overkill. Why don't we just calculate the electrostatic force? Why don't we just use Fe equals kq1 q2 over r squared? And why don't we just call it a day with that? Why don't we just use that in order to figure out, how all these effects are going to happen? Well, remember that equation only really works at its simplest form for point objects, objects that are very small, or spherically symmetric objects, objects that can be reduced down into a point object, objects that are spherically symmetric, that, circles. Or spheres, since we're talking three-dimensional. However, there are lots of other different alignments of charge you could have. You could have a line of charge, you could have a ring of charge, you could have a rectangular prism of charge, you could have a sheet of charge, and those objects, that would be a lot more complicated to use the electrostatic force equation. Matter of fact, you'd have to use some pretty intense calculus. That's not what we're about here. What the electric field does, if we know how big the electric field is for a particular object, then what we can do is we can use that and a charge that might come in and interact with that electric field and actually measure the electrostatic force that would be on it without even bringing that object in. So the electric field, it's kind of like a backdoor method for calculating how much force might be on an object in situations that are more complex than simply 2-point charges a certain distance apart. So we're going to be focusing on how to measure and draw electric fields. This first video, we're going to focus on how to draw electric fields. We represent electric fields with vectors. Okay, electric fields are vector quantities. And the vectors are called electric field lines. Since they're vectors, we want to measure the magnitude and direction of the electric field. In order to kind of imagine how an electric field might look, we do a thought experiment. We come up with what is called a test charge. A test charge is a hypothetical, very small amount of charge that does not affect the field itself. So think about like a proton. It's small, it's positive, it's not really going to affect the field of some larger distribution of charge. So we pretend that, hey, let's put a proton here and let's predict what would happen to it. Let me show you what I mean. Here's is a large distribution of positive charge. Imagine that we put a proton right here above it, okay? Now, in our heads, the way this thought process works is, let's imagine what would happen to that proton if we just let it go. Well, there's a proton here, a very large, that's positive, a very large positive charge down here. We know that positive charges will repel each other. So if this positive charge, the big one, is locked in place, but the proton is free to move, it's going to get repelled away from this charge. So what we're going to do is we're going to draw a vector in the direction that the proton would experience that force. If the proton would experience the force upward, if it's right here, then we're going to draw a vector pointing upwards. Notice that the vector starts on the charge that we're trying to draw the electric field for. Okay, the whole point of this, right, what we're trying to do right now is we're trying to draw the electric field for this positive charge, and we're going through the thought process of how that would look. Imagine if we put the proton over here. Again, positives repel each other. The proton would be repelled to the right. It would experience a force to the right. That's why it would move. It would be repelled that way. So we draw another line starting from our charge in this direction. We could do the same thing down below the positive charge and also to the left. Matter of fact, anywhere that you go on this charge, the proton would get repelled straight away from the charge. Like so. I could keep drawing lines, but typically when I'm drawing electric field lines, I usually stick to about 8. The Regents might tell you something different. They might say 3 or 5. I like to draw about 8, just so I have all my bases covered. So notice it doesn't even particularly matter, actually, the direction, as far as the direction goes. It didn't matter where I put the proton. I could have put it here, or I could have put it here. In either case, the proton's going to get repelled in this direction from that particular spot. If I put it here or here, it's still going to get repelled to the right. So what we've just drawn is a map of the electric field, okay? We've drawn vectors representing the direction that the proton would move in, the test charge would move in, if we were to just leave it there. I totally said that wrong. We have drawn the direction that the test charge would experience a force in if we were to just leave it there, okay? If you put it here, the force will experience it to the right. What we did not draw, this is why I just messed up, what we did not draw is the direction the proton moves. Because imagine if I put the proton down here, but then I kind of like, and as I'm letting it go, I kind of like pushed it down. Well, the proton's going to get forced out this way, but it's also going to kind of move down. So I don't want you to think that the electric field shows the direction that something moves in. It specifically shows the direction of the force that would be applied if a small positive charge were put at that spot. The direction of the electrostatic force. Let's move on. What if instead of a big positive charge, we had a big negative charge? Let's put our proton right here. Protons are positive. Negative charges and positive charges are attracted to one another. They're not repelled this time, they're attracted. So what would happen to this proton? It would want to get closer to the negative charge. It would experience a force pulling it in. So now I have an arrow that points inwards. And the same could be said for any location on around this particular charge. At any point, the proton, if it's just a proton and a singular large distribution of negative charge, the proton is going to be attracted to that negative charge. All these electric field lines point straight in. So what we've done right now is we have just seen the electric field. These are electric field configurations for an isolated positive charge and an isolated negative charge. You need to have those memorized, okay? Notice that the positive charges, or the field for the positive charge, points straight out away from the positive charge. All the vectors begin on the positive charge and point straight away. For the negative charge, all the field lines start out at infinity and they come in and they end with the arrow on the negative charge. Okay? These two are very easy to remember. A couple other things that we want to think about. Where is the electric field strongest? Well, this is kind of I think probably an obvious question. Is the electric field going to be strong close to the charge or farther away? Probably close to the charge. That's what I would assume, even if I didn't know this already. And in addition, where are the field lines closest together? In other words, if you were like traveling and you were recording how much time it took or how much distance you had to travel between each field line as you were going over, if there were like bumps on like a little car track or something, in closer, the field lines are closer together, closer to the charge, the field lines are closer together than out here. You'd have to travel farther distance. This is not a coincidence. It turns out that the closeness of field lines should tell you how strong the electric field is. And that's something that's important to remember for when we see pictures of electric fields later on. So again, electric field lines, what they do is they show you the direction that a positive test charge would experience a force if it were at that location. We could draw even more electric field lines than this, but I stopped at 8 because you kind of get the picture after a while. If there was a test charge right here, it would experience a force straight out. We could draw in another line there. All right. I kind of already mentioned this, but just to reiterate, remember that field lines do not show the path that the test charge takes. They don't show the direction it moves in. They show the direction it experiences a force in. Okay? That test charge could show up on that near those charges, but it could have an initial velocity which would change which direction it moves. However, the force that it experiences is not going to change based on if it has initial velocity or not. Think about Fe. It's kq1 q2 over r squared. Nothing in there about velocity. Okay? So the electric field lines show the direction that the test charge would experience the electrostatic force in. They only show the direction of Fe at some location. Also, the length of field lines does not mean anything. It has no meaning whatsoever. I could have drawn all these lines very short, like in about this area. I just chose to draw them long because we had enough room on that picture. The length of the field lines means nothing. Another thing that we went over, field lines start on positive charges, as in they point away from positive charges, and they point towards negative charges. Because remember, the field lines are showing the direction of force for a positive test charge. Positive test charges are going to be attracted to negative charges. Field lines should never, ever cross. That would imply that a certain location has two different directions for electrostatic force, and that is impossible. Okay? It's impossible for a force to have two different directions. I'm not talking about two different components of the same force. That's just writing the force in a different form. I'm saying you'll never have a situation where the electrostatic force points to the left and also completely separately points down. That wouldn't happen. Okay? It would be kind of like saying I am both 12 years old and 19 years old. Well, no, one or the other is true. Okay? You're either 12 years old or you're 19 years old. Okay? The electric field line should never cross because that would imply two different directions for the same force. Okay? Forces have one direction. Breaking something up into components is a completely other topic, but forces have just one direction. Let's look at a couple other examples that you need to know, different scenarios. In total, there's 6, okay? But really, if you can remember 4 of these different patterns, you're going to be all set. What if instead of just one positive charge, you have 2 positive charges? Well, I think we could probably assume, let's say we put a test charge over here on the right-hand side of both charges. It's going to get repelled by this charge and by this charge, so we could pretty much assume that the electric field line is just going to go this way. Same thing over here. Put it to the left, it's going to get repelled by both. And I think we could probably assume fairly reasonably that if we put a test charge directly between the 2 charges, but maybe closer to the left than the right, we know that the electrostatic force is proportional to the inverse of the square of the distance between the charges. So that means that the closer it is to a charge, the stronger the force. The smaller the distance, the stronger the force. That means if you put a little test charge here, okay, closer to the left-hand charge than the right-hand charge, it's going to get repelled very strongly by this charge, not as strongly by this one. So the field line would point here. You would add those 2 forces, big force from the left, going this way, smaller force from the right-hand charge, going this way. The particle would end up experiencing a force to the right. Same thing if it's closer to the right than the left. There would be a field line going this way. Right in the middle, if it was exactly equidistant between our 2 charges, you could imagine that those 2 forces would cancel out and there would actually be no charge right in the middle. It gets a little bit more complicated if we kind of go off this center line. Let's imagine a test charge right here. It's very obviously going to experience a big force, a big repelling force from this charge. Not so much from this one. So initially, the force as it starts to move out would be in this direction. But as it moves away, as you move farther away from this charge, the force from this charge will weaken. Okay, if you put a test charge out here, it's not going to experience as strong a force. And look, you're kind of starting to move closer to this force. Okay, this charge would put a force on this test charge in this direction, but weaker than if it was in here. This particle would put a force on this test charge in this direction. But as we keep moving out along this line, the force from this charge will get smaller, the force from this charge might get larger. What ends up happening, and there's got to be a better way to show this, so maybe in class we'll take a look at some stuff and we can see why this actually happens. With 2 charges, what you start to see in these sort of off-centered ones is that the field line starts to look curved. It starts to do this sort of thing. Okay? And what that's signifying is the force from the 2 charges, okay, is actually changing. At each point along here, we are adding up the force from this charge and the force from this charge. And we're adding 2 vectors that those forces represent together, and the curved part is kind of the sum of those vectors. We're getting at different locations here, we're getting different results for the direction of this force. So if you want to know the direction of force, let's say right here, you would look and you'd kind of take like a tangent line sort of approach. The direction would be different for a test charge up here because now you've moved a different distance away from each charge. The nice thing about this is it is symmetric. The same thing happens over here. You have kind of this curved line, like so. And it's also symmetric down this way. Again, these are not paths that the particle would follow. These are directions for field lines. It's the direction that an object would experience a force in. And we're not saying that the direction of the force is curved. We're not saying it experiences a curved force. Vectors are always straight lines. What we're showing is that if you were to follow this line, the direction of force changes. Okay, in close to this charge, the direction of force is in that direction. Okay, pointing out this direction. As you go along that line, if you were to go along that line, the direction of force, the combined force from both charges, changes. Okay, let's do another. You could imagine that up here at the top of the left-hand charge, you would experience a force going upwards. But as you move away from that force, or from this charge, the force from this starts to play more of a role because this force is going to be decreasing. The field line out here looks kind of like this. In a similar pattern, starting from here, those field lines look like this. It's not super important right now that you can explain exactly why all of these look exactly like this, but you do need to get the picture right. You do need to be able to draw this picture, or at least select this picture on, like, let's say, a multiple choice question. What if we have two negative charges? Well, it's kind of the reverse. If you have a positive charge off to the right of both negative charges, it's going to be attracted inwards. If you have a charge that's in between, a positive test charge that's in between them, it's going to be attracted to whichever one it's closer to. So we're going to have arrows like this. In the middle, it would be equally balanced, so nothing. No force at that point. The other lines, these curved lines, are just the exact opposite. They're just in the exact opposite direction as these were in. And again, the reason that they're curved is because as you move along the field lines, not saying the particles move along the field lines, but if you were to move along the field lines, the direction of the net force for the two particles would change. In close, it almost looks like it's straight lines, but as you get farther away, due to the effects of two charges, they kind of curve in different directions. Okay, I think I've drawn those right. A third charge distribution that you need to be aware of. Okay, notice that again, just like with the single positive, single negative, okay, these are just kind of the inverses of each other. The arrows are just pointing different directions. Same thing right here. The arrows are just pointing in different directions. Now, what if there's one positive and one negative charge? Well, let's start out here. If we have a positive test charge here, it's going to get repelled by this charge, attracted to this charge, but since it's much closer here, that force is going to be bigger. This is just going to get repelled to the left. For this negative charge, if we put a test charge right here, it's going to get attracted to the negative, repelled by the positive. But since the negative charge is so much closer, the arrow is going to point that way. Again, notice the arrows are starting on positive charges, ending on negative charges. And then finally, if it's in the middle, well, if it's in the middle, it's going to get repelled from positive, attracted to negative. That's a field line that looks like that. Okay? So it's already looking a little complex. What if we have a charge that starts up here? Test charge. It's going to get repelled away from the positive, but as it moves farther away from the positive, it's going to start getting attracted to the negative. That's going to curve the field line around like this. The same thing's going to happen down here. Think about it, right in the middle, we kind of have this flat tangent line. It kind of ends up getting a little flat right here. That implies that this particle is trying to push it up and to the right, this particle is trying to pull it down and to the right, it ends up just moving to the right. And if we look at other places on here, like if it starts from the top, it's going to do pretty much the same thing. There's just going to be a little bit more bowing out of the charge. Matter of fact, out here, these are still going to loop around. I'm just going to kind of draw them as heading off into infinity. These eventually would loop around and connect. Again, it's mostly important that you can recognize the patterns at this stage. Okay? Just to kind of summarize what we have so far, look at how close together the lines are, close to the charges. The electric field lines, or the electric field, is strong, close to charges, and it's 0 in the middle. Same thing applies here. It's strong close to the charges, is where the field lines are close together, and it's 0 in the middle. Out here, again, notice we have lines that start on positive charges, end on negative charges. Okay, except for the ones on the outside. These field lines are never looping back around, but every other one would. Okay, let's see here. I'm going to actually stop the video right there. We're going to talk about this example in the next video.